Dominic, well, you gave me this. Dominic is a colleague of mine in the design division here at the UW. He teaches industrial design and design studies. His research focuses on new methods of manufacturing, and he has a nice website called humblefacture.com, which I'm sure he'll mention and tell you about. So thanks for agreeing. He's going to give us a kind of overview first.
Yeah, so thanks for having me, guys. I am super excited about digital fabrication, mostly because it puts the power in your hands instead of in the hands of Sony or the hands of Google or whoever is going to make your next greatest thing. You can make your next greatest thing, so you don't have to wait for them. Do it yourself. We're going to take a little safari, right? Imagine that you are, I don't know, imagine that you're Richard Attenborough or something, and we're cruising through the Galapagos, and you've just come upon this place. Now, if you've ever been to the Galapagos, you might know that there are tortoises and stuff there. If it's your first time, it might be a little daunting, so I'm going to go pretty quickly. We've got a lot of ground to cover. We're going to explore all of the different sort of organisms within this ecosystem, right? We've got some little maker bots down in the foreground, and some like CNC mills flying through the sky. Looks like a Epilogue Laser 8 little mini mill over there. So basically, why am I so excited about this fabrication technology? Well, it's functional, right? You can make real things. You can make stuff that actually does something, rather than making stuff that looks like it does something, the way that industrial designers have done for 30 or 40 years. We make pretty renderings and it's vaporware and it just goes away. You can make good stuff, right? It's precise enough that you can actually make a mechanical device, a linkage, a gear. You can make something that functions. And you can actually make stuff because it's relatively affordable now, right? I'm going to show you some parts that I made for a project recently for about $10, $20 for real parts that are like real housings for a real cell phone, right? And the best thing is, it's shareable. So we can all make our stuff. You can make stuff that I design. I can make stuff that you design. Somebody can make stuff that somebody they didn't even know designed. And I'll show you an example where before Matt and I met, he had made something that I designed. So it's a giant space. And in the last, I don't know, maybe 2 or 3 months, it's gotten a lot gianter. Ever since Brie Pettis and the MakerBot team really started pushing this stuff, and they had a lot of help from the RepRap team, which had been pushing stuff prior to that. This idea of fabricating things has really taken off, and Make Magazine has jumped on it, and even some sort of more mainstream media have jumped on it. Fast Company also recently ran an article about this stuff. So it's getting into the collective consciousness, and that means that not only are commercial enterprises like HP talking about developing a new 3D printer that's going to be in your house, but open source people like the MakerBot or like the Candy Fab here you see. These people that are just interested in making something weird are going for it. So we're going to try to explore this stuff within a framework. Within that framework, some of the technologies are closed, proprietary, and some of them are more open. When I say open, it's not really open source in the traditional sense because these are objects, so it's not like you can just share the code. You have to share maybe the description of the object. You have to make it in a way that's accessible to people using a laser cutter, using a mill, and you maybe have to make it out of materials that people can actually afford, so like plywood instead of titanium or something like that. So I'll call that out with the Creative Commons logo, even though Creative Commons maybe applies, maybe doesn't. And like any ecosystem, there's an easy way to break it down. I've cut it into 4 sort of phyla, I guess you could say, or hierarchical bits. There are some technologies that you use for creation. There are some technologies you use for translation. There are some you use for fabrication. Those are the ones that most people really get fired up about. And then there are some that are maybe, I think, most important that are for proliferation, right? So it doesn't matter if you just make it yourself. It matters more if a whole bunch of people make it. So let's start off with creation, right? The first thing you need to do if you want to digitally fabricate something is you need to describe it digitally. And there are a number of different ways you can do that. In order to describe it, you have to think about what is it going to be made out of or what machine is going to use it. Many machines that we'll talk about work with a 2D file, right? And that's a Cartesian, a set of points on a plane that describe a shape or that describe a line. Doesn't get into 3 dimensions, but you can cut it out of a 3-dimensional surface or object. Some of those that are open are Inkscape, which you may know is kind of a competitor to Illustrator, but it's fully open source. It's a little sketchy, as far as actually making real fabricable objects, and it doesn't have very good measurement tools, but it is open, and it is improving. There's also QCAD, which is an open source version of a closed source product. It's a little finicky to work with, I have to say, but it's a very solid CAD package compared to Illustrator or compared to Inkscape. And then the bottom row, obviously there are hundreds of closed source proprietary CAD packages. Illustrator is one that many more industrial design or graphic design type people will be familiar with. AutoCAD is one that maybe architects and engineers will be familiar with. There are also specialized types of 2D drafting software like EagleCAD, which is used for making traces for circuit boards, right? So if you're specifically designing a circuit board, it has all these routing features and things that will allow you to make that a lot easier than if you tried to lay out a circuit board in Illustrator, for example. Let's say that you're going to 3D, though, right? So 2D was just the surface. Now, if you're getting to 3D, you have to think about how do you deform that surface into a 3D object, right? How do you enclose a volume? And one of the easiest ways to do that is with a mesh. A mesh is a system of vertices with little lines connecting them and then planes going in between the lines. So it's like, 4 lines define a square, and you have a bunch of squares around, and that forms, you may have heard of polygons in a video game. Those polygons are polygons of a mesh. And meshes are really nice for video games. The problem with meshes is that they aren't as strong at describing things like, okay, when you make a hole, for example. You make a hole in a mesh, you cut a hole in one surface, and you cut a hole in the other surface, but it doesn't know anything about the volume of the mesh. So we'll talk about some software that's better at making holes. Meshes are actually what people learn to use first, though. Most of the time when we teach stuff in school, we teach students Rhino 3D because it's pretty intuitive. It uses a special kind of mesh definition called NURB, which is a little smoother, but it's a pretty, small distinction, tight distinction. As far as open options go, you have Blender, which is an amazingly powerful program. It's also designed in a way that's different than a lot of the 3D programs that people have grown up using, so there's a lot of frustration with it. But it's actually pretty powerful for getting started, and it's free, and it's open. So you can write your own scripts to improve it. You can do lots of stuff to change it. Wings 3D, Art of Illusion are Wings 3D is more of a modeler for surfaces, for kind of characters, and Art of Illusion is more like a, boxy primitives modeler, shape modeler. Both of those are great for the things that they're great for. None of these on this first page are very good for really precise things, right? Other than SketchUp, which I put on its own line because it's not really open source. It's free from Google, and you can extend it with scripts, but you can't really hack it completely. And so, and it's unclear, how much Google is going to keep supporting it, or how much maybe they're going to make people pay for it at some point. So SketchUp is really great, and it has really nice measurement facilities, but it has some of its own problems. And then the bottom line is these more professional, hardcore grade packages that really get you started. But again, they're mesh modeling, so if you're going to buy 3D Studio Max, which is $3,000 or more, you may as well buy Pro Engineer, which is $3,000 or more, and you'll get some more function if you're interested in making a thing. I should mention, all of the links and this presentation are going to be up on Humble Facture within the next couple days, so you don't have to be feverishly taking notes. I would much rather that you guys pay attention and think of good questions to ask me rather than just trying to write down every word I say. Okay, so we're done with meshes. Meshes are interesting, but they're not as powerful as solids, right? So the difference between a mesh and a solid is the mesh is just the surface. A mesh model doesn't know anything about what's the inside and what's the outside, and often can get that wrong to horrible problem when you try to print it on a MakerBot, for example. Solids know which side is the inside and which side is the outside, and so when you do Boolean operations like saying make a hole, into here, or even better, take my head that's solid and hollow it out to a thickness of whatever. Solid modelers can do that with no problem. Mesh modelers often have huge problems doing that sort of thing. And those are the kinds of things we want to do, right? Because if we want to make the shell of a product like this camera that we're recording this with, that looks like just a shape, right? But really, it's a very thin shell with a bunch of guts inside of it. And you would like to be able to describe the shape and then shell it out without having to describe all of these, surfaces and whatever. Solid modelers will allow you to do that. Unfortunately, there hasn't been a lot of work done in the open community with solid modelers. The military, and I cannot remember, I think it's the Army, developed a solid modeler for making tanks and then opened it. And as you can imagine, it's military wear, so it's really, really powerful and hopelessly arcane. BRL CAD is unbelievably complicated to use. Most of it is command line based. It exists in about 30 modules that are all, it's unbelievably complicated to use. If you are a programmer and you want a really cool project to make a front end for BRL CAD that will make somebody like me able to use it, you would have worshipers, not even joking. Heeks CAD is another relatively recent offering using a framework called Open Cascade, which is sort of like BRL CAD. It's an underlying way of modeling objects, and then Heeks CAD is like a front end for that underlying way. It's also pretty new and not very powerful yet, compared to SolidWorks, Pro Engineer, or Solid Edge, which are unbelievably powerful pieces of software. Most of the objects that you use, sewing machines, vacuum cleaners, toasters, were probably modeled on these software. So they're very powerful, they're very expensive. They also take a decent amount of time to learn. There's another kind of emerging group of 3D modeling software that are less concerned with describing an object and more concerned with making a complicated mathematical description of an object. And this is sort of nice for people who are, one, interested in math and visualizing math, or two, already programmers. So for example, OpenSCAD or OpenSCAD is a command line based sort of scripted solid modeling language. So you literally describe every object with code instead of with a graphic interface. That's really weird for somebody like me who grew up using graphic interfaces in Photoshop and Bryce 3D and whatever. But for somebody who is used to coding, it's great. It's awesome. You have complete control, and it's really powerful. So OpenSCAD is a wonderful thing. TopMod is what's visualized here, or pictured there. TopMod allows you to take a mesh and perform mathematical operations on it. You don't have a lot of control over moving the points of the mesh, so you can't smooth things or do things the way that you would use a modeling program like Wings 3D or like Blender for. But you can make unbelievably complicated sort of permutations of that mesh. And so, for example, this was sort of parametrically defined from a soccer ball mesh that was started out with, and then they performed operations on all the vertices and slowly built up this sort of fractal shape. And the cool thing about rapid prototyping technologies is they let you print something that is as hopelessly impossible to print as this, right? This is an amazingly complicated object that it would take some hobo 300 years to carve out of a piece of wood or something like that. But it prints in just the same amount of time as a ball of plastic would print on one of these printers. You can see another example here where this is a series of sort of interlocking tubes of, weirdly bent and interconnected tubes. If you look up Bathsheba Grossman, there you go, bam. Everybody knows Bathsheba. So Bathsheba Grossman is a woman who does really amazing sculptural stuff using TopMod, using her own proprietary software. So she's worth looking up. She's on Shapeways, which is a site I'll talk about a little later. If you want to go full-on math, Sage is sort of an open version of Mathematica that allows 3D output through, you can actually like directly code all of the stuff that you want to code to make your mesh. That's a pretty complicated route if you don't use it on your own, so I wouldn't recommend it as the start, but you could do cool things like, creating a solid that was based on the sound from, if you wanted to do translating data into art, that could be a way to do it. All right, so we've gotten through creation, right? We're done making our physical model, or our 3D model, and now we want to get it sort of set up so that it could be made into a physical model. The trouble is, most of these machines, so the MakerBot, the Mendel over there, if you use a Stratasys, if you use any of the machines I'm going to talk about later, all of them take different formats of file, which is one thing. Many of them require a file that has some specific characteristic. In STL files, which is what the MakerBot prints, one of the things that's really important is that the file be manifold, which means that no one chord is shared by more than 2 adjacent faces, which basically means it is like a balloon, where there's only one surface and it fully connects. If you can imagine a balloon with a hole in it, that's not manifold and not watertight. So it can't print that because it doesn't know what the inside and the outside is. The inside and the outside. If you had a balloon intersecting a balloon, right, where one of those edges of the balloons is actually shared by 4 surfaces that are coming in on the intersection, right? This is getting kind of complicated, but in any case, it can't print that either because it doesn't know what's the inside and what's the outside. And that's one of the problems with that surface modeling, right, is that the inside and outside are poorly defined. And so you have to check for whether it's manifold or not. So one of the ways that you do that is in cleanup, you check maybe you're going to have extra points that got created when you did a 3D scan or something like that, and they're just sitting off in space, and they're just going to gum up the machine. Maybe you have non-manifold vertices or non-manifold faces. In MeshLab, which is this piece of software, which is open and free, you can check very easily. You can perform culls of errant vertices. You can check to see what vertices are manifold or not. You can select them. You can change. One of the things that happens is the normals of the surface, so the direction the surface faces. Basically, the surface's cheap way of saying this is outside and this is inside. You can flip the normals. So you can say the whole outside is the inside and only the thing in the bubble is the outside. And that would print really poorly, right? It would fill up this whole volume with plastic and have one bubble of not plastic. You'd rather not do that. So you can flip the normals, the correct way. So MeshLab is awesome for that. MeshLab is also pretty light on your system. So if you have OpenGL acceleration, MeshLab will run really fast, and you can preview models in it, whereas Blender takes up a little more system resources, so opening Blender just takes longer. But Blender also has some nice checking features. So another thing you might want to do is you might want to take your 3D object, and maybe you don't want to print it on a plastic printer. Maybe you want to make a pillow that is the shape of your 3D object, right? A pillow is kind of cool because it surfaces, or maybe you want to make a shirt, right? This shirt, this sweater that I'm wearing, which isn't a very good example, but if this was sewn together and not knitted, this is a bunch of surfaces that are flowing around a 3D shape. And if you broke the seams and unfolded those surfaces, you would get something that looked kind of like this, right? You get a pattern. And then if you take that pattern and you weld it together, this is made of steel, if you weld it together in the right way, you'll end up with a 3D thing that's hollow. And the cool thing about it is it's makeable with scissors, a printer, and if you wanted to make it out of steel, you'd have to cut it with a plasma torch. But if you wanted to make it out of cardboard and tape, you could cut it with scissors. you can become the 3D prototyper. So that's one of the things I'll talk about is how can you do this without having to buy a MakerBot or without having to buy buy something from Shapeways. So this is one option, is to use an unfolding program. SketchUp has an unfolder script that is available if you search for SketchUp unfolder script. Some dude on a forum wrote it, and it's amazing, and it's really intuitive and easy to use. You can unfold almost anything. Some things get weirdly convoluted, and you have to kind of unpack them or break them apart. If you want to go one step further, a guy named Paul Haberle used to work for Silicon Graphics, wrote a piece of software called Lamina, which does a much more elegant job of unfolding a 3D model. It can even do pretty nice approximations of doubly curved surfaces, so like a sphere. You can, draw little cut lines, which will allow you to unfold a sphere, which, as you know, is pretty complicated if you think about unfolding a globe. So those are really good options. Rhino 3D can do some unfolding. It's medium, I would say, and it's also proprietary, so you got to pay for it. Another thing that you might want to do in translation is make a toolpath, right? So when you are printing out one of these objects, rarely do you just sort of automatically go and the printer just spits the whole thing out at once, right? Instead, it has a nozzle or it has a print head that goes back and forth or around a path and squirts out a little bit of material, or uses a laser to sinter together a little bit of material, right? And then all those paths add up to the part. Maybe it's using a knife to cut away some material. So SkeneForge is a piece of software that's used by the MakerBot to actually go in and slice up your STL file into toolpaths, right? It will output toolpaths for you, so you don't have to go in and hand draw them bit by bit. Pleasant 3D is a tool for visualizing those toolpaths, basically. SkeneForge is not very good at doing that, but Pleasant 3D can visualize it. And then SketchUp Slice Modeler is another option. I'll show you some slice model things, but basically SketchUp Slice Modeler will take a volume and will let you place slices of cardboard or of plywood or whatever in kind of a crisscross pattern that defines that volume. And I'll show you an example later. It's pretty obvious when you see it. So, okay, you've done your creation, you've done your translation. Great, you got a file. Now we're going to fabricate it, all right? And this is where the real interesting stuff happens. This is also where you need to make a choice. You need to think about, so your virtual file was just that, a virtual file. It was a description of what was possible. It will only be as strong as the fabrication process you choose. It will only be as clear, translucent, as the fabrication process you choose. It will only be as electrically conductive as the fabrication process you choose, right? So the process you choose is really crucial. In most cases, you could make any of these files with any of these processes, or many of these processes. So for example, you could print it in candy, you could print it in copper, you could print it in plastic, you could print it in jello, right? You can print it in whatever you want, but what comes out is going to vary depending on what machine you print it on. I want to start with, remember way back at the beginning we were talking about 2D description? 2D patterning is kind of underrated. You all have printers, you all use those printers to print stuff every day. You don't think about how awesome that is, right? You're already digitally fabricating something. You don't have to send a description of your illuminated manuscript to a monk and have them copy it out laboriously and it comes back years later. You get this thing fast. And in a lot of cases, you get it made out of something that has physical quality, that has physicalness, right? It actually is a physical thing. A laser print is made of plastic. It's just made of very thin plastic. And so, if you want to make a printed circuit board, you can look this up on, anywhere. Type in laser printed circuit board. That's actually how I got this image 20 minutes before the presentation, because I was going to have another image there. But you can take laser print and you can iron it on to anything that won't melt, basically. If you take a laser print and put it on acetate, you can even get special laser print transfer paper that's kind of waxy that will release the laser print toner. You can iron it onto copper printed circuit board material. You can iron it onto styrene, and then you can vacuum form the styrene. You can iron it onto wood pretty easily if you want to put little like labels on an art project or something. You can iron it on. You can iron it onto fabric, depending on how open the weave of the fabric is, and depending on how much toner you want to get on the thing. You can iron it onto a variety of different things. So really think about that. That's a real thing. This print or this image on the left or on the right is an image of a microfluidics device. This is 1,000 micrometers or micrometers. Is that micron? Micrometers or picometers? Who knows? Micrometers. Awesome. So 1,000 microns. That's tiny, right? That's a really, really small mixer. And you can see what's happening is they're feeding in blue and yellow ink at the top, and they're creating a gradient of different concentrations of ink. And this is important because if you were interested in making a lab on a chip that did tests of DNA or did tests of urine for steroids or something like that, you could do it with this pattern. This pattern was cast with a very interesting process. This woman at UC Berkeley developed it and realized that you could laser print on shrinky-dinks material, which shrinky-dinks is this stretched plastic. You guys have played with this when you were kids, right? You put it in the oven and it shrinks up. You could laser print on the shrinky-dink, and it's already laser printed really small, and then you could shrinky-dink it by 10 or 20 more times, and you can get down to a micro scale shape, right? This is almost like making silicon yourself, right? Patterning computer chips yourself, except you're doing it with shrinky-dinks. It's insane. And so she's published like 20 papers based on the shrinky-dinks thing. This is changing. It's changing the world of microfluidics, because previously you had to use like laser ablation. You had to use this $200,000 equipment, and now you use an Epson printer for 20 bucks, 50 bucks, whatever it costs to get a laser printer and some shrinky-dinks paper or plastic. So this is huge, and I really think this side of the fabrication stuff has sort of fallen to the wayside of the hacker community. So this is good stuff to think about. Also, patterning, right? Still 2D. We're still going 2D. This machine, a computer-controlled embroidery machine, is capable of doing all kinds of crazy stuff. You can put conductive thread in there. You can pattern on Tyvek. You can pattern a water-absorbing thread and use it to print something, right? You can actually make real things using a computer-controlled embroidery machine. So don't sell your sewing machine short. This is Hector, is a paint bot. It's basically 2 motors with big long strings and a spray can that has a servo actuator. And this allows you to paint a whole wall as big as you want, as big as you have string, with a computer following Illustrator paths. Right? This is a simple thing to build. People have built this and rebuilt it since the original one. And it's an amazing way to paint a giant wall with just this one device, right? Very different than the printer you're probably used to. This is another thing, this idea of integrating, right? Taking something and changing it around, not really cutting away from it or adding to it, but just changing the way it's organized. And so this is a computer-controlled knitting machine. You guys didn't know that knitting machines existed? Maybe you did. I bought a knitting machine on Craigslist for like 50 bucks. It's not computer-controlled, but I can still mess with it. But they've rigged it up so that it prints, these shirts are actually prints of people killed in Iraq. Like every time the news prints a new headline with a Iraq death or something in it, it automatically prints these t-shirts. And so it's like this record. So this was this crazy art project that somebody wanted to do, but it's using this amazing technology for digitally fabricating an object. Finally, you get into cutting, 2D cutting, right? You can cut vinyl using a vinyl cutter. You can actually get this done at sign cutter shops, at FedEx, at Home Depot. You can use that vinyl as a resist for screen printing if you want to print a whole bunch of things and you don't want to burn a screen yourself. You can use it as an actual surface on something. You can use it as a sticker. but it also has physical thickness. So there is a 3D prototyping system that uses this roll-in sign cutter and cuts out layers of sticky stuff that you then stick together. It's unbelievably expensive and sort of time-consuming, but you know, it worked when I was an undergrad. That was one of the things we used. Now there's better stuff. The Craft Robo is a sort of consumer version of this Roland, much more high-end cutter. But this is, I don't know, maybe 500 bucks, 300 bucks? I don't know if anybody has played with this thing, but this will output any path from Illustrator. You can cut it out of cardboard, you can cut it out of cardstock, you can even cut it out of aluminum foil if you're careful with how you stick it down. So get these things and mess with them, right? Oh, okay, so there's another, we've got 2D cutting with a knife, with a router, like a PCB cutter, which is supposed to be, there we go. So this PCB cutter on the left was developed by an MIT student, and I am forgetting his name, and that's awful. Jonathan Shakler? Oh, that's right. Yeah. In any case, he made this PCB cutter, so rather than etching, using this etchant, this chemical etchant, his cutter just mills out the copper. And this cutter is fully open source. You can download all the plans. It's cuttable using a ShopBot, which is this guy on the right. ShopBot is basically a router, which you've all maybe used in your home shop, attached to a Cartesian bed that can go more or less in two directions. It has a little bit of height adjustment, but it's mostly for cutting out shapes. And you can cut out of whatever you want, whatever the router can cut. You can cut out of plywood, you can cut out of MDF, you can cut out of your own homemade, ironed together plastic bag crap. I don't know, like, you know, whatever you throw at it and it can cut in 3D or in 2D. You can cut using a laser, right? So every time we're stepping up, right, with a knife, you probably couldn't cut very thick stuff, probably couldn't cut, you know, metals, except maybe aluminum foil. So every time we step up, we change the stuff that we can make. We change the function, the potential function. Router, we can cut thicker stuff, but maybe it has to have rounded edges because it's a router, so it has some thickness, right? Laser is really narrow, so you can cut really like precise, detailed little things. But depending on the strength of your laser, you can only cut certain things. So like this is a I think it's like a 3 watt or 2 watt laser. Maybe it's a half a watt laser that some dude rigged up with 2 scanners that can only cut cardstock, and it can only cut it at a rate of like 1 minute an hour or something like that. So it's basically for marking on cardstock. It's a fun project. It doesn't really do much. The epilogue laser, or competitors, Matt has one at Metrics, those can cut things relatively thick, about a half inch or a little more in wood, and various thicknesses in paper and that sort of thing. But they can't cut metal. They can only really engrave the surface of metals. And then if you get up to a really hardcore laser, you know, like a 300 watt or a 600 watt laser that can go through, you know, thicknesses of maybe a 1/4 inch of steel. Those are used by the metal cutting industry to really get detailed parts relatively quickly. And you can find places in town that will do that sort of fabrication for you. Most of them are getting to be more open to people in the community. And then you get up to the really hardcore stuff, right? So we're kind of going from least crazy to most crazy. Waterjet is capable of cutting through almost an unlimited thickness of stuff. Get a little bit of variation at the bottom. You can see here they're cutting through like 6 inches of granite. And it's very precise. Like it's a tiny little jet of water. If you have a granite countertop, chances are it was cut using one of these. It is the way to cut stone because it doesn't wear out. There's also a technology called wire EDM. This is generally used for very high precision parts. It uses a wire, and so if you search for EDM or electrodynamic machining, you can find a make video where this guy talks about making a homemade version. And basically what you're doing is you're using electricity to rip metal ions off of a metal substrate and then flush them away with an electrolyte. So you're putting a salt solution. You can see this liquid here, and that blue is an electrical arc. And there's a wire, and then flush them away with an electrolyte. So you're putting a salt solution. You can see this liquid here, and that blue is an electrical arc. And there's a wire that's continually going past the wire. It's very thin and very conductive and very corrosion resistant so that it doesn't break. And they're running a ton of current through that, ripping off ions from the metal and actually eating the metal away. And you can machine down to like a hair thickness slot in like a dime. It exerts no force. That's the coolest thing about this. So if you want to make the most precise part possible, wire EDM is absolutely the way to go. It's much more difficult to get set up because the people that do it like to do it in huge quantities and with reputable people. But this kind of pressure from us, right, is what's going to open the community, is what's going to open us to these kinds of manufacturers. Also, people messing with doing this kind of thing in their home, making a DIY one of these. The cool thing about it is all you need to have is a pretty precise control system. There's no, it doesn't use exotic metals for blades or high-powered lasers or anything like that. You can use most of the parts and make them yourself. And then a plasma torch cutter, people are probably familiar with if they've taken a metal shop class, uses a plasma arc to melt the metal and then air to blow it away. And these can be really easily controlled with almost the same setup as the shop bot. Instead, you've got a cutter that can cut metal. So those are pretty cheap and they're pretty accurate. They're not quite as accurate as either of these, but the cheapness makes them awesome. So if you want to get something plasma cut, CNC plasma cut, you can absolutely look it up in the yellow pages. There are people, especially custom motorcycle shops will do a lot of this stuff, both water jet cutting and plasma cutting, if you need to get some fabricated. So this is probably the type of fabrication that people are most familiar with, is carving, right? Actually removing material. Carving is nice. You waste a lot of material, usually. So you start with a big thing and you carve it down to a little thing. It's also not as easy to control the, if you want to carve a thickness of something. So like, for example, the housing of that camera, right? We want it to be really nice and thin. Once you carve off one side, you have to think about, well, how am I going to carve out the inside, So it gets complicated to think about making complex parts. But making things like reliefs, like this is the ShopBot, which I said it has a little bit of up and down travel. This is a carving for a door, and they've got like an eagle, chilling on the door. It's great for that. It's awesome for doing these very intricate carvings for inlays for your house or whatever. A CNC mill is a pretty common thing that people will have. It requires a little more. It requires a little more input, honestly. Like you need to be a pretty skilled operator to run a CNC mill. So that's sort of the trade-off. Is it's very easy and accessible to just stick anything in there and cut it, but you got to have some smarts to run it. It's not like sending something to Shapeways. I keep pointing over there. I've got some examples of Shapeways sending a file to this service, and they just send you back the part. And then here's a CNC foam cutter. If you have a hot wire, you can cut styrofoam with that hot wire. If you have a CNC rig, you can move that hot wire in a controlled way. And so you can cut a 3D shape or a 2D shape or a computer-controlled shape. This is actually a giant screw that's going to be cast in steel. If you ever wondered how they make those huge screws for ships and things, usually they cut them out of foam or out of some sacrificial medium first and then invest it and then burn it out and cast in there. All right, so another cool option for you guys, and something that you can do with scissors, again, right? Because you've all got printers or access to printers, and you're all able to slice something up because you can use either the SliceForm plugin here, or you can just output using ScaneForge or using another slicing software. You can just output slices. All of these projects here were done using a 2D cutter. So in this case, this is stacks of $1 bills that were cut sequentially so that bits were removed. I don't know if you can see here. The eyes of this skull sort of like dip in, and this was cut on a laser cutter. They cut sequential bills and then sort of overlaid them to form this 3D shape. Similarly here, this is just cut using, this is acrylic, and they just cut it on a laser cutter, but you could easily cut this with a jigsaw, with a bandsaw, with scissors if you're cutting it out of cardboard, and you can make a 3D shape, right, by layering things up. Finally, this one was cut using that slice form plugin in SketchUp, right? Somebody imported this cone, and then they said, put a bunch of slices this way and a bunch of slices this way, and the plugin puts all of the thicknesses of curves so that they'll slide together, flattens them all out, lays them all out on a page. All you have to do is print it. It's the most amazing, wonderful thing. You're gonna love it. So yeah, and then you just get it printed at Kinko's, right? Divide up the file in a PDF and then get it printed at Kinko's and cut it out. So we get to layer addition. So right, previously we've been doing carving, taking stuff away. Here we were putting layers together, 2D layers together, right? Here we're gonna put layers together again, but we're gonna put them together bit by bit. So you can hear that guy going, every time it goes and changes its tone, that means it's moving in a different direction, slightly. Excuse me. Or it's moving around the outside profile. But a lot of times it's just going back and forth, putting down a little bead of material. It's almost like when you were a little kid and your elementary school teacher, right? You didn't just squirt a big blob of glue in the middle of the piece of paper. You were supposed to go back and forth and cover it up nicely. That's sort of what the MakerBot is doing right now. And it's slowly doing that, and by the time it gets done with one layer, that layer is cured, is hard, because it's not melted anymore, and it goes back and puts another layer. The RepRap Mendel is a fully open, but also fully, 60% self-replicating device. So basically, Matt has this guy here. Once it is all put together, it will be able to print 60% of its own parts. And then the remainder of those parts will be able to be purchased at Home Depot and McMaster-Carr, so you don't have to custom machine anything. This MakerBot is actually printing, I don't know if it's printing it right now, but okay. So this MakerBot is printing a part that the Mendel needs to get going. So we're basically using this machine to build that machine to build other machines, right? The reason that the MakerBot was created, actually, was because the Mendel is awesome, but it's a chicken and egg problem, right? You can't have everybody have a making machine if you don't have enough making machines to make all the machines for everybody to have a making machine. So the MakerBot is a machine you can buy for pretty cheap, and it works well enough to make all the parts for the Mendel. It doesn't work as well as the Mendel. The Mendel has a lot more build area, and it's a lot more precise. But again, the MakerBot is sort of like the cheap printer that every computer company gives you with your thing, just so they'll buy the ink or whatever. That's actually why HP is probably getting into the 3D printer business. And then this is a Stratasys printer, which is sort of the more high-end commercial version of this exact machine. So it prints in exactly the same material. It has sacrificial layers, so it can print slightly more complicated stuff. I don't have an example there. This is a monkey head that was printed using the MakerBot. You can come take a look at that after stuff. The object printer is sort of a hybrid weird printer. It actually prints like an inkjet, but it prints, I think I actually have, I don't know if, I may have it later, but it prints clear, right? It photo cures the polymer after it lays it down, so it can be clear. Semi-clear, translucent. I don't know if you guys can see. Sort of translucent. Take a look at those. But so the RepRap and MakerBot are both open source. The Stratasys is very expensive and not at all. And when it breaks, you will know how closed source it is. We had one break in the department, and we couldn't even change the hard drive out on it. ourselves. We had to have them come and change the hard drive, which is ridiculous because it's literally just a hard drive. Anyway, don't even get me started. Another type of printing is printing with powder. So we were printing with layer addition. This is sort of powder addition. Powder prints have some issues in a lot of cases because they are brittle, because they're just powder, right? They're not actually continuous lines of anything. These prints from the MakerBot will tend to come apart at the surface where they were MakerBotted together. Powder prints will tend to just break sort of arbitrarily, unless you do things like Mark Ganser does, and I'll point to him in a second when I show some of his stuff, but he's faculty on campus who's developed some very interesting powder printing methods in other materials. So the Z-Corp machine uses a cyanoacrylate ink binder. It's like super glue, more or less. And when it prints into acrylic. So it turns into acrylic. It's medium stiff, but the cool thing is you can have color, right? So it's great for people who want to make molecules. I think this is anthrax, the protein that kills you when you have anthrax. These are some various DNA or protein folding models. It's a horse head. They can print very detailed parts. This is actually a ball bearing that is fully working and printed all together, right? So all you do is you sort of brush out the powder from the part, and you end up with this beautiful, immaculate piece that really is not that functional. It's just very visually accurate, right? So Mark Ganser and others have developed ways to print powder with a binder, right? Like cyanoacrylate, Mark actually uses a mix of, I think you're still using alcohol and sort of gummy stuff in the print, right? So they use their lab on campus is developing these open source formula for the powder. So this powder costs a ton, right? Very expensive, and you have to buy it from Z-Corp, and it's a racket, right? Yeah. Yes, yes. Talk to the gentleman behind you. Yeah, exactly. Yeah, so you don't. So that is the key thing. You actually don't need to use the special business. So I think Mark started using a system that I think it used just like flour and clay, or I don't know, some food chemicals and clays and ethanol, more or less. And by mixing those things together, you get a reasonably solid object that you can hold and use just like the proteins and stuff and see, oh yeah, that looks cool, right? But then they took it one step further, and you can actually bake the clay. So this idea of sintering the powder print, right, actually sintering it together, you can fire the clay, and it shrinks a lot because it's missing all of that binder material because it burns off. But it's still, now it's ceramic. And so he's got some examples back there that you can browse around. He's got a whole box full. But you can glaze them. You can infill them with silica, so they're a little stronger and more waterproof. This is another example where they used a glass powder bound with, I think, like dry egg whites or something like that. So you mix this powdered stuff together, and then you hit it with the alcohol, and there's the actual part, or another one of the actual parts, printed in glass, right? So that it comes out really soft and weak and useless, and then you fire it, and it turns into glass. It melds together into glass. I don't even know what that one is. There's another glass. Oh, so this one is a vitreous, like a fused vitreous glass, right? So this one is more porous because all of the binder burned out. But now Mark has figured out that if they really nuke it in the kiln, they can form a flowed vitreous film around the outside, and it will actually be shiny, like you would expect glass to be. And it will also be waterproof, which is wonderful, because you don't want your wine leaking out the side of the thing, right? Also, when you see metal prints, most of the time, metal prints are actually sintered or infiltrated something. So in the case of Shapeways, Shapeways takes stainless steel powder, prints it with a binder, fires it at a high temperature to burn off the binder, and at the same time packs a bunch of bronze filings around that, and the steel acts as a wick and sort of sucks up the bronze. So you end up with a very bizarre composite of stainless steel powder with bronze around it. It's awesome because it looks like metal. It's not awesome because it doesn't really behave like metal. It's very difficult to grind or mill because it's stainless steel and bronze, right? It's like this weird mix of kind of a composite. So if you want it to be like that, it's awesome. But if you're not so, Mark, you've got your hand up. There's another, sorry?
There is another material you can use that doesn't have any usable.
Oh, awesome.
Next one utilizes colored gold.
Awesome. Okay, well there you go. So this is the coolest thing, right? Is that once the technology is out there, once the idea is out there that, hey, we can print this thing and we can stick it together for just long enough that we melt it together and then it's real, then people start printing all kinds of crazy stuff, right? It would be wonderful if, for example, you could print simultaneously glass and metal, because then you could have a 3D circuit that was able to conduct like a manifold in different directions. That would be amazing. Somebody's going to do it. Maybe you're going to do it, right? It's been done. There you go. So it's already been done. Fabulous. But so those are the kind of things that I want to get your brains cooking about, right? Powder printing can get really weird. You can use a beam of heat, right? So we previously used a sintered binder, blah, blah, blah. But if you're using a beam of heat to just melt the stuff together, you can start to do things like just melt metal straight next to other metal. You could do selective laser sintering on plastic, so this is a kind of HDPE/nylon plastic, but it has cellulose fibers, really small cellulose fibers in it, which makes it a lot stronger. This is flexible, which is not very common for these rapid prototype materials. It's very flexible, actually. And because of that, it's a lot more durable. Because of the fibers, it's a lot more durable. The reason you can do it with the fibers is because of that laser is sort of indiscriminate. It's just melting them all together. You can also use a very lo-fi heat source. This is just using the candy fab. You guys may or may not know about the candy fab. Prints in sugar. Sugar's really cheap, which is the reason that they wanted to use it. So they've got a bed that's like 2 feet by 4 feet by 2 feet. They can literally print like that big of a thing. It's insane. It's ridiculous. So you can see this is a giant, giant print. Probably like, I don't know, 10 pounds of sugar. You know, just this solid thing. The other thing that's nice about it is it smells like a donut shop, you know, or a candy store as you're printing. It prints using a heat gun from a desoldering setup. So a very concentrated but blown source of heat. So it's not even a laser. It's really cheap. So, okay, we went through powder prints. There's one more 3D printing method, and that is light cure, right? When you're curing with light, that's like stereolithography. You may have heard of stereolithography. Stereolithography uses two lasers that are UV, and neither one of them has enough energy to turn the resin in this big tank into solid, but together they do. So if you cross them, you sort of make a solid piece of resin inside a tank of liquid resin. So the cool thing about it is you're able to make very intricate parts because it's all supported by this resin. The bummer of the thing about it is you need two UV lasers, which are, up until recently, were not very cheap. Even now, SLA is still a pretty expensive rapid prototyping process compared to some of these other ones. So the Objet printer, which is this one, uses SLA resin, but it uses a light, just a light to cure it, and it lays down the resin with the inkjet printer, basically. So it prints a layer, and then cures that layer, and then goes up and prints another layer and cures it at the same time. So it doesn't have to use the laser, so it can just use UV LEDs that are cheaper, or a UV lamp. And that's the Objet printer there. Most of these prints will look like this. They'll look clear, because the light has to get to them, right? So that's great if you want it to be clear. If you don't want it to be clear, it's a bummer, right? So that's the thing, is that there's no right printing method. There's no best printing method. There's only the best method for whatever you're printing. Yeah. Okay. There's one, just a couple more. So, I wanted to include one more really bizarre, crazy, weird method of assembly, and that's this self-assembly. So, this is a machine that was developed by some students at UW. I don't know if any of you are here. Awesome! Holy shit, that's fabulous. Sorry, holy cow. This is a Lego-based DNA or any sort of laboratory liquid pipetter, right? For transferring liquid from some bulk material into a test. And so you can do DNA experiments. One of the things that you might do is sort of fabricate DNA in such a way that it folds up in shapes you want. So the cool thing about this, and this seems really outlandish, but this is a smiley face that is microns across, made from DNA, nanometers across, tiny, tiny, tiny molecular smiley face. You could make this smiley face in your house. This is the only kind of nanofabrication that you could possibly do right now, and you could do it. Like, that's what's so awesome, right? You could build this sequence of DNA through a series of experiments, and then you could do the reaction that would make it fold into a smiley face. If you wanted to. You need to figure out what you're going to do with that, right? But this is nanofabrication in your house, in your garage. The last bit, and I'll go through this fast. Again, all of this will be up on Humble Facture, so you can really check these out. Making one thing is what we used to do. Making lots of things, but only one person making it, that's what we do now, right? That's mass production. But anybody making everything is what's the future. And the reason that we're going to get there is by having these different technologies for sharing. We need to have swap meets like Thingiverse. 3D Content Central is made by SolidWorks. It's another site for sharing more technical files. This is a skull that I made from an MRI scan of my head. And I uploaded it to Thingiverse. I didn't have a printer. I didn't get to print it until the fourth print. But Matt printed it even before I got to print it, right? And I didn't even know Matt. Matt printed it from, down the street, across the country. Somebody printed it in aluminum. My skull in aluminum. How cool is that? Right? Some dude I don't even know. He emailed me and was like, dude, I printed your skull in aluminum. I was like, awesome. Send me a picture. Put it up online. So it's amazing. This is totally amazing, right? Another awesome option is fabbers that you don't have to own the machine. So you don't have to have this thing humming away in the background, in your garage. You could go to Pinocchio and get things laser cut and sent to you. Relatively inexpensively. They have a whole variety of materials. You can go to 100,000 Garages, which is a lot of shop bots around the country that will cut things out of plywood for you. You can go to Shapeways and get these. These guys cost me about 20 bucks total for these two parts. This was about 40 bucks. These are two housings for a phone concept. Hacktories are awesome, right? These spaces to be in. Jigsaw Renaissance, super badass. Well, I don't know where Jigsaw Renaissance, yeah, in the back, word. Sorry, I saw you slapping. I don't know you yet, but Jigsaw Renaissance is awesome. Metrics Create Space is awesome. Places to be, to do this stuff. Now, I want to talk a little bit about the future. Wider availability is awesome, but we can't do one in every house. HP's model is broken. We would have so many printed awful things gumming up the works. We need to think of some better way for sharing just the right specifications so you can have the right thing, not everything, right? We need to have better materials. We need stronger, more reusable materials. It would be cool if you could grow your own materials, right? Why do you have to use plastic? We need to bridge this nanoscale divide. That's why I bring in the DNA. It would be so cool if you could make your own circuits. And I'm talking about microchips, right? But you need some way to fabricate them, and you can't afford to have a giant silicon plant. And finally, we need some new model of ownership, because if, you can see what's happening to books, you can see what's happening to magazines. ID Magazine went under a couple of months ago. Things are changing, and things are going to change the same way with objects, unless we figure out some good way to keep that stuff rolling. But most of all, we need more participation. I would love if all of you guys went out and fabbed something yourselves, right? I would love if you would join me at humblefacture.com, comment on stuff. I write a lot of different things about a lot of different things. You can look on Thingiverse at what I've been making, Thingiverse/Dmuren, and you can follow my Twitter at Muren. Thanks so much, guys. Good question. So on the DNA thing, can you build organs? It turns out organs are pretty complicated. Unfortunately, there are a couple of people working on interesting stuff. If you look at Carnegie Mellon is doing a lot of work with printing organs. So you make a structure and you implant it with cells that are like stem cells, and then they can sort of grow into the organ. It's unclear whether you're going to be able to do that yourself in the next 10 years, but maybe. I'm not even, like, it's so on the edge. Literally, the first printed anything, and this was like cartilage in an ear or something. I mean, it was like the most simple organ. The first printed anything was 3 years ago, and now they're printing kidneys, like trying to print kidneys, right? They're not actually implanting them in anybody, but they're trying. So go for it. Any other questions? Yeah.
When you talk about using an inkjet printer, a couple of years ago, we had a contracting company downtown. They do DNA research.
Right.
They developed technology for studying DNA by using a laser printer using an inkjet printer to print like 10,000 microdots of 60-inch pairs on a piece of glass.
Yeah.
And then they react that and use a light.
Yeah, totally. Yeah, so if he's talking about DNA microarrays, right? Microarrays like this microfluidics, like that little mixing capillary tubes. Microarrays are this huge technology that's really going to change the way that we test for diseases, especially genetic diseases. It's going to allow you to very quickly, put a blood sample on a glass plate and immediately see, okay, there's a signal, there's a signal, there's a signal. Those genes have lit up. Those are printed. If you look up DNA microarray online, you'll get more information than you need. But those are printed using inkjets, right? They're printing the DNA on glass. And that was some dude in his garage, figured that out. So go for it. Rip it up. Other questions? Yeah. What does humble factor mean to me? Good question. So I'm interested in this, in all these technologies, insofar as they enable individuals. I'm not so interested that they're all using plastic, right? And so that's one of the reasons why I'm really pumped about technologies that allow us to make things using simpler materials, more complex things using simpler materials. So getting at it in a more humble way, right? Getting at technologies that are on the scale of society instead of these giant, we have to partner with China in order to get all of our electronics. That seems out of the scope of regular human interactions, like you and me interactions. I would love to be able to make my cell phone with us, rather than with thousands of people that I don't know and I don't know their situation, right? And I'm just not able to. So those are the technologies I'm working on, is like, how do we make more stuff together in our small local area, but not sacrifice. I don't want to go back to living in a cave, right? I like being on the internet. Are there other questions? Yeah, Nick. So there's two. So Nick was saying, am I talking about localizing everything with less outsourcing? Is that sort of what you're saying?
I'm really excited about this idea of everybody being able to use this.
Right.
Why? Why are you excited about this?
Okay, why am I excited about everybody being able to manufacture stuff? I think that the problems that come out of products in society, so when we talk about child labor in somewhere, or when we talk about pollution, e-waste, right? E-waste is a big thing, or the plastic in the ocean. I think that those problems come out of a lack of personal agency to change the situation. If you buy a computer, you don't have a choice. If you want a computer, you have to buy a computer that's made a specific way. You just don't have a choice. And I think that that choice is sort of fundamental, the way that, no taxation without representation gives you a choice. There's a reason that we got all riled up. I think that you should have no fabrication without representation, right? I think that we should have a greater hand in the things that affect us, the physical objects that affect us. I think that those physical objects constitute speech in the same way that posting billets and bills in 1700s constituted speech. And I don't think that we should be restricted anymore. So it's sort of a political thing, honestly. But I think it's a very real thing, right? Like you guys should have the opportunity to realize your lives in the way that you want them to be realized. Not that you would make everything, but that you would be able to have it be made the way you want it, instead of having to, to accept what Steve Jobs thinks I should have.
I think it's a good place to stop there.
All right?
Thanks,
Thank you
Dominic.
guys so much.
So we're going to take a quick break, 10-minute break to reset. But before we do that, I just wanted, since there's about 5 times as many people here as we expected, literally, I'd just like to get a show of hands to some questions, and maybe some of my Overlord colleagues can count. How many first time at a Dorkbot meeting? Okay, so especially for you people, we're curious about how you heard about it. How many just from our website or email lists? A few. Where else? KUOW show that Eric was on. How many of you are UW affiliated somehow, students, faculty, whatever? Dub list, did some of you hear about it from Dub? Where else? Any other sources?
Live Journal.
Live Journal? Just out there.
Kirkland Arts Center.
Kirkland Arts Center, wow. DIY bio. So, just the word is out there, and it's an interesting topic. Any other sources we should know about?
Other people know on the Makers Club list is the Bates Club and the Northwood Promise.
I didn't hear you. Maybe you can tell us afterwards. Viral, yeah. Just in the blogosphere and the Twitterverse. Okay, one other housekeeping thing at the end. If everybody who borrowed a chair from another room could please try and take it back where you found it. Otherwise, I'm sure I'll get flooded with complaints from other faculty in the building tomorrow, and we don't want to jeopardize our status here, because we're being sponsored very nicely by the department. So please just try and put things back where you found them at the end. So 10 minutes and then we'll reconvene.